Hi, my name is Ansha, and I'm an SDE with Alexa AI within Amazon. Within Alexa, we focus on providing as close to real-time data as possible and enable machine learning use cases at scale. Our belief is that providing real-time transforming computation on streaming data will provide greater value to Alexa as a whole by unlocking faster ways to train, test, and release production models to provide delightful customer experiences. Today, I'll be talking about a platform we launched within Alexa called the Continual Learning Platform and how we're leveraging Apache Flink using Kinesis data analytics to power the streaming aggregations and transformations. In this presentation, we'll cover the following. First, a background on what continual learning is, an overview of the platform that we built for Alexa, how we leverage Kinesis data analytics and Apache Flink, problems that we solved for some of our use cases using the platform, challenges that we currently face, and what we're working on next. To understand what continual learning is, we'll first go through what continual learning isn't. A machine learning model is a large statistical model that makes predictions and is built by showing a black box algorithm millions of inputs. As shown in the picture on the slides, in batch offline training workflows, we generally do the following steps. First, we train the model on a large set of data points. Second, we then validate the model using data points that the model hasn't seen before to verify the correctness of the model's outputs. Then we deploy the model in production. And finally, we monitor the performance of the model. Once the model performance degrades, the model hosted in production is refreshed. In order to refresh the model needs to be retrained. And that's frequently done on all the full historical input data. So now that we know what continual learning isn't, we can talk about what continual learning is. In continual learning, models are trained and retrained in a continuous way. The input data that is continually refreshed and the models that are only retrained on a subset of the data instead of the entire history. So in the picture shown on the slides, you'll see a new arrow from the deployed model in production to the trained model, showing that the input data for training is constantly refreshed at some cadence. Continual learning is advantageous to us for primarily two reasons. The first is adaptability to changing trends and usage, and the second is for cost reduction. So for adaptability, by training models on a smaller amount of data that's available more quickly, we're able to train models faster and get them into production. This allows us to react to changes in customer requirements and behavior. For instance, during COVID, customer usage patterns changed significantly, and continual learning workflows can allow us to quickly refresh models to provide the best experience possible to delight our customers. Whereas in batch offline workflows, like the one shown on the screen, teams have to spend a long amount of time on retraining because models are retrained on the entire historical input data set. Second, for cost, continual learning-based systems give us additional opportunities at cost reduction and saving because we don't need large data sets for training as we're continuously refreshing our models. Furthermore, we do not need to pay for long data retention. So we spend less on compute clusters due to a reduction in the amount of data that's processed compared to batch offline workflows. Next, I'll talk about how our platform works. First, data stream from the Alexa runtime to a data lake, where a specific subset of interactions are then available within about 10 seconds of the customer interaction with Alexa for applying a transformation. This group of transformation services are shown on the slides in the green box. The users of the platform are then able to perform a user-defined transformation in SQL, Java, or Python on a window of events in a purely configuration-driven way. Users are all able to optionally perform streaming inference on the data using SageMaker inference hosting endpoints. In other words, Alexa teams just provide a Docker container with a model artifact and easily perform inference on the stream within Kinesis data analytics Flink applications. Data is then streamed to a data store, an online or offline feature store that can be accessed for retraining, inference, evaluation, and analysis. We decided to use Flink on top of Kinesis data analytics for a few key reasons. The first is that Kinesis data analytics Flink applications makes the process of generating windows on a streaming data very easy. Given that we're interested in improving customer experience, and that requires inspecting usage patterns, we want to be able to look at the past few interactions that a user had with Alexa and execute some business logic, and do this at scale. Flink makes generating these windows very easy with built-in window operators and an interface for extending ones with custom logic. Prior to using Flink, in order to find the last couple of interactions, we would need to have a large fleet of EC2 instances with a lot of custom logic to express each use case. For each new use case, we would need to add more custom code, introducing engineering dependency for scientists and modelers. Our usage of Flink with its easy windowing through a SQL statement increases our scientist and modeler self-sufficiency to launch new features themselves by expressing these through simple SQL statements. Second, Flink allows us to transform raw data streams into other representations. The data that comes out of the raw streams like text and audio needs to be massaged into other representations. Our scientists and modelers like to play around with different representations of that data. For instance, scientists take a textual representation of an interaction with Alexa and then turn it into an embedding to use in a training routine. Finally, Kinesis Data Analytics Flink applications allows us to focus on use case logic and not infrastructure. We do not have to manage our own application hosting infrastructure. Instead, we can define our business logic for launching use cases. This allows us to provide a force multiplying experience to accelerate near real-time streaming, inference, and transformations within Alexa while minimizing the engineering capacity that we have to invest handling operations. Next, we'll talk about some problems that we've solved for use cases on the platform. I'll be focusing on the benchmarking model performance and how we easily guardrail Alexa experiences in production using feedback detection. First, I'll cover some background about how Alexa uses feedback to provide more delightful experiences, and then cover how those computed metrics and statistics are computed on the platform. Alexa provides a variety of proactive experiences, including end of dialogue, by the way. To determine what content to show customers across these channels and guardrail these experiences, the systems need data about Alexa's past customer interactions to decide which proactive experience to offer, and data after an interaction to analyze how it went in order to optimize future experiences. For example, Alexa uses this information to make more personalized decisions about whether a news or weather experience may be more appropriate to display. This also allows us to guardrail model experiences and attributing a degraded experience to a particular model in near real time and take fast action to improve the end-to-end customer experience. Our platform users can generate streaming inference transforms that label data near real time to detect feedback types. So using our managed machine learning inference hosting solution, teams can spin up Flink applications and use their ML models to attribute feedback as a particular type like unprompted or customer-initiated feedback. That data is then used to update and optimize experience via telemetry service. So as you see on the slide, teams are able to easily spin up Flink applications using Kinesis Data Analytics through a control plane and specify their business logic. And using their machine learning models, they're then easily able to generate these streaming labels and combine them to form and attribute feedback to particular experiences. With our successes using Flink on the platform, we also face a couple big challenges in abstraction and simplification of the platform components to increase adoption, as well as providing data flow transparency to users of the service. Because Flink requires that users be familiar with streaming concepts like windowing operations, there's a steep learning curve that makes scientists less willing to use the platform. Furthermore, because there are many service components within the platform like SageMaker inference hosting, teams are required to familiarize themselves with a large vocabulary of managed underlying components. In addition, data flow transparency is another challenge that we face. Visualizing data flow through the tasks and operators within Flink requires a lot of context knowledge. Because there are also interactions with additional services like inference endpoints, tracking data loss is difficult. Over the next year, we're going to double down on the success that we've had using Kinesis Data Analytics and Flink to replace components within our data storage. In our offline storage layer that saves data to S3 buckets that are then available to query in bulk, we currently leverage many AWS services to stream aggregate, partition, and persist data to a dataset. We're going to simplify that architecture to use Flink applications for aggregation and partitioning. In our online storage layer that we use to retrieve data quickly, we use many AWS services for loading and saving features to the data store. We plan to improve the experience and speed that we can add new features by moving the pre-materialized views to the Flink application. In other words, we'll be able to perform roll-ups, so calculations aggregated over a past amount of time, so the past 7 days, and additional pre-computation logic to features, eliminating additional calculations that are run during services runtimes prior to usage in an Alexa experience. This will allow us to use more features to provide a more delightful experience to customers. Thank you for watching the presentation.